What?
Spaghetti accelerator.
Number
13.
13.
We accept the challenge.
아, 네.
Number 13. Now please write down your name. please.
Honorable juries and fellow commentators, I'm the reporter from Team Self-Years, and today I'm going to report problem number 13, spaghetti accelerators. And this is the problem statement. When a piece of spaghetti is pushed into the bend tube, small debris of spaghetti may be ejected from the other end of the tube at surprisingly high speed and investigate this phenomenon. And we will mainly focus on what is the mechanics behind this phenomenon and what relevant parameters will affect the phenomenon. And this is our report outline. And first is the observation part. This is our experimental setup. As you can see, there's a bending tube, or we want to call it accelerators. And we make one side of the accelerators clear so that we can clearly see what happens inside the bending tubes. And this is the force gauge. We put the force gauge contacts the 3D printers so that the force gauge can push the spaghetti in constant force, a constant speed. And we also make a special joint to make sure the force gauge will push the spaghettis vertically. And the force gauge will be like this. And this is the observation videos of our phenomena. As you can see, the spaghetti will bend in a tube and break into pieces and accelerate in supersonic high speed. And this is the chart to proving that. As you can see, the velocity of the spaghetti goes from a nearly zero in very low and suddenly accelerate to a very high speed. And we only capture the highest speed so that the air drag won't affect on our analysis. And next, we'll move on to the explanation. First, when the spaghetti enters the bending tube, the tube walls will generate normal force and causing the spaghetti to bend. And the spaghetti will also store elastic potential energy while bending. And as the normal force exceeds a certain threshold, the spaghetti will break into pieces, and the potential energy will mostly transfer into the kinetic energy. And because the mass of the spaghetti pieces is very small, so the kinetic energy will generate very high velocity. And next, we are going to talk about the fracture precision. Due to the deflection equation, we can see that the fracture precision will only related to the beta, which is the bending angles. And if we bring the analysis into the counter-reverse spin equation, and we can see that the length of each friction will roughly be the fixed value. And next, we analyze the force. And as you see the last frame before the spaghetti ejects, you can see that the spaghetti is actually contact with 2 points. And if we push the spaghetti into the bending tube, the 2 contact points will generate the normal force, which we made it N1 and N2. And if we draw the coordinate axis, and then we can separate the x components and y components. And after some solving, and we can finally get the N1 and N2 force. And this force we can all measure by the force gauge and tracker. And then we calculate the potential energy. This formula describes the integrating of the value in the whole spaghetti's elastic potential energy. And if we separate the 0 to B and the B to A, then we can get the final elastic potential energy formula. And then is the energy transition. And because the elastic potential energy will equals the kinetic energy and the fracture and also the friction. So we times the alpha, which is the convert ratio, to represent the losing energy. And after some solving, we can get the final velocity formula. And if we make the alpha to be 1 and bring back into the formula, we can get this theory line. But as you can see, the theory line didn't matches our real experiment data. So after some calculating, we can get the alpha is nearly equals to 0.75. So approximately the 25 of the energy is converted into fracture energy and heat energy. And next is the analysis of ejection speed. And first we measure the Young's modulus. And because we use the same spaghettis in our experiment, so the Young's modulus will remain the same. And if we calculate the if we draw out the stress strain diagrams, then we can bring the slope of the stress strain diagram into the Bernoulli series and calculate the Young's modulus. And next is the measurement of friction coefficient. First, we made the long pipe walls, and then we release the spaghetti pieces from the top of the pipe walls and let it slide through the pipe walls. And to make the simulator relate to the real situation in the bending tube, so we simulate the spaghetti motions in 2 interfaces too, and hence the measured friction coefficient is significantly higher. Then next, we also measure the fracture length, and as you can see, as the angle of the bending tube goes higher, the length of the spaghetti will be smaller. And next is three our relevant parameters. And first is the pushing force. As the bending moment increases, the stored potential energy, when the stored potential energy is higher than the negative work of friction, then the spaghetti will eject, and increasing the pushing force related to the higher ejection speed. Then the second parameter is bending angles. As you can see, when the angles of the bending tube is higher, the curvature will be higher. So the bending so as the bending moment increase, the stored potential energy will be higher than the negative force of friction, and increase the bending angles to be higher ejection speed. And next is the friction coefficient. And as the friction coefficient increases, we can see the negative work done by friction will also increase. So it will make the lower ejection velocity. And you may ask why the theory line isn't perfectly fits our experimental data. And it is because the error increased with the friction coefficient too. And the effects of the normal force is also amplified. So the fracture spaghetti is no longer only affected by the N1 force. So we bring the K value introduced into the adjust of the theory line. And if we bring the K value and we calculate it, the K value will roughly equals to 0.79. And then we'll move on to the discussion. First is the emitted directions. We will focus on the curved parts of the spaghettis. And when the spaghetti starts bending, it will cause the elongation and the compressions. And the stress on the outer side of the spaghettis will dominate the directions. And from the tube walls will adjust the directions and causing the proceed along the tube wall. And that is a fun fact. Why does the spaghetti breaks into 3 pieces? And the answer of this is because the snapback effects. The spaghetti won't break into in the same times after one segment breaks. And it will repeat these snapbacks, and the vibration affects the other segments. And so the spaghetti will break into 3 or more pieces. But why in our experiment we didn't see the spaghetti breaks into 3 or more pieces? It's because the spaghetti, the wall of the bending wall will because the bending wall will decrease the snapback effects. Okay, then we'll go to the conclusion. First questions in our main focus. Why does the spaghetti enters a curve to and shoot out? And the answer is spaghetti will bend and store potential energy in bending tube, and if the normal force is too strong, and it will break into pieces and turn the potential energy into kinetic energy. And the second question is, how do we calculate the emitted velocities? We use this. Well, first we analyze the forces and the bending moments, and finally we fit in the convert ratio, and the velocity will be nearly the same to our experiment data. And that's which coefficient and the fracture length and the Young's modulus and the friction coefficient is the parameters we change in our experiment. And we can see the pushing speed is positively related to the velocities, and while the bending angles and the friction coefficient will be negative related to the velocities.
Comes up.
And this is our presentation.
Thank you for your report. Thank you. Okay. Can you explain how to do the chart?
Okay.
How to do the chart?
We calculate the velocity of the spaghetti by tracking, and we just draw this.
Which point you chart? The top of the spaghetti or bottom?
We track the front of the spaghetti.
Okay, thank you. And then using how much point where the spaghetti touch the spaghetti? How much point you see the spaghetti touch the spaghetti?
We only have one spaghetti in our institute.
The next question, and what is the formula come from?
The formula comes from we integrate every value of the spaghetti that installed the potential energy, and integrating it, then we can get the formula.
Okay, I found the museum and this cover statement, and I will focus on raising height speed and how the experiment reflects the spring high speed. And next, and according to the discussion, we use the potential energies to explain why the spaghetti will eject from the pipe, and then has a formula to associate it. And equipment use a sensor to push the spaghetti through the bending house, and again the friction with the condition will reflect the result of the experiment. And the result, you didn't see the spaghetti banking into the many place in the experiment, so the potential energy can into the okay. Can you like the within the experiment, have you collect the bending spaghetti?
You mean the little business?
Yes.
As you can see, this is the 10-angle bending tube ejecting spaghetti pieces, and this is the 25-angle ejected spaghetti pieces. And as you can see, the length is very different.
Yes. And using how the size of the bending angle will affect the speed of the spaghetti when you just one time.
Can you rephrase the question?
How the different mass of the spaghetti affects the speed of the spaghetti when you bending from the pipe.
We calculate the mass of the spaghetti. We consider the mass of the spaghettis, and we calculate the kinetic energy of every bending angle spaghetti pieces. And as you can see, there's a chart. It's supposed to be a chart, and we calculate it, and although the 25 bending angle spaghettis will be shorter and the value will be smaller, but the kinetic energy generated to let the 25 bending angle spaghetti will be bigger.
Okay, that's it. And don't mention so. Okay, according to your formula, the energy change is like this, but okay, like this. Can you translate something? Why the tension of the formula don't consider the friction between the pipe and the spaghetti?
Yes, it consider. It is considered in the calculation of the.
Okay, can you mention anything? How to get the free value about exponential speed? Where exponential, how to get that? Which motion to get the
Can you rephrase the questions?
the value of the level and exponential, right? How to get the exponential value?
We calculate. We analyze many experiment data, and finally we find that the alpha is nearly equals to 0.75.
Oh, yeah, percent. But how to get data? Using the data and get a way, right? How to get the data?
What do you mean? How to get the data? We track. We capture the velocities. We capture the observation videos and we track the velocity out.
How to do the simulation?
Simulation. We find it on the website of the reference.
Do you think why the simulation have a big difference from the relative condition?
I mentioned it in our report. Because when the spaghetti will break into multiple pieces, it's because the vibration of the spaghettis. And in our experiment, the bending tube is very small and squeezed. So the spaghettis, the bending tube will decrease the vibration of the spaghettis when breaking.
Oh, temperature is going to be okay. How to change the bending angle?
Bending angle. We use 3D printers to make the different angle bending tube. As you can see, the bending tube like this is 10 degrees bending angles, and like this is 25. Like this is 25 angles of the tube. So you can see a big difference between this.
Yes. And okay, before the spaghetti flying from the pipe, using power it to compress the
Okay, replace.
how you power the spaghetti compress the pipe when it fly out from the pipe. When it from the fly out from the pipe, how to compress? Just a electric pipe or they will touch the wall of the pipe.
Do you mean what spaghetti will act when ejects through a pipe?
Yes.
Jurors can we use the black hole? So this is the bending tube, and the spaghetti will bend kind of like this in the tube. And as I mentioned in my report, the spaghetti will attach two sides of the tube. And when the spaghetti breaks, and the spaghetti will eject, and this is the part where the friction will affect the spaghetti. And so the spaghetti will actually kind of like bouncing around and ejecting from the bending tube.
This is the pumping point is the pumping point is close to another possible way and using the effects the result when before the spaghetti fly out from the pump.
Do you mean if here attach the
Yes, just push it to it. I think it will touch here.
the reporter wrote that this won't cause the spaghetti. This will not affect the spaghetti's eject speed.
Why?
because we use the pushing force, right? And the pushing force measure the force, and because the force is nearly be the same, so when the spaghetti ejects, it will only let me rephrase my answers. Because of the spaghetti, the force that the spaghetti ejects is because the elastic potential energy that stores in the spaghettis. So when the spaghettis eject, the elastic potential energy will transfer into the kinetic energy, and the energy is stored in like here. So this part won't affect the spaghettis.
Yeah, but we will change the angle of the top and some condition. This actually will bonding layer, right? We'll change the angle of the.
No, the spaghetti will bouncing like here.
Some condition that the bonding will disappear. We're going to change the.
No, every experiment we analyze is the spaghetti will break after the bending angle part. So this part won't cause any effects to the spaghetti ejection.
Can you condense the formula and the experiment result?
We bring the data into the formula and calculate the potential energy. And the potential energy, that's and after we have the potential energy, we can calculate the velocity of the spaghetti. And the velocity of the spaghettis will nearly match the data after we put the alpha, which is the convert ratio, in our theory.
How do you get the very real?
What do you mean?
The
Value?
very yes. There is data to get experiment view and I have to get a very real.
What do you mean? Can you explain more?
What is the very view of the very view? How to draw the prima here very view? Very view.
We base on the theory line. So the theory line will match the experimental data, so that we can say that the theory line, our calculations and our theory is matched to the experimental data. So we can say that this is right.
Opponent summary, please.
Okay, I have a suggestion from to the reporter. Maybe he can show more experiment data there, many people to clear now how to get a chart, and I think it's a very good experiment spaghetti. He bring the bending spaghetti to there, and then I can clear now how the condition change the result, and it has the spaghetti photo to see what happened there too. And I think it's very good. He used the simulation to explain the theory. And as a suggestion, he can show us the code of the simulation, let us to understand why the simulation work, and explain where the formula
Time is up. Review, please.
So my first question is, from the observation, you can see that there's clearly rotation and spinning after the injection. So have you accounted this in your kinetic energy from the transfer from potential energy to kinetic energy?
Yes, because as we draw the pictures, the spaghetti will actually bouncing and ejects out of the bending tube. So the kinetic energies will also include in the.
Okay, thank you. So why don't you test? Why don't you point the dot at the center of mass of the spaghetti during the launch, for the second spaghetti after it's launched? Why do you test it in front of the spaghetti and instead of the center of mass?
Because if we track in the middle of the spaghetti, and the spaghetti is like all yellows, so we can track in very
Okay, thank
perfect.
you. What do you think?
Because it's a very small type, so you can measure that.
Okay, so next, you applied the cantilever beams equations, correct?
Yes.
However, I noticed that you also mentioned there's 2 points that's differentiating from each other. So therefore, in order to apply cantilever beams, you have to have one fixed end. Do you acknowledge that?
Yes.
But however, from the experiment, it's clearly not. There's no direct fixed end for it.
Yes, we make one point fixed.
Okay, thank you. So this one is for both of you. Let's start with the opponent. How do you think the initial velocity will affect the final velocity?
And still the 3 point there,
You think there's 3-point bending?
yes, yes.
Okay.
3 point convex.
Oh, okay. Then what do you think?
Can you refresh the?
How do you think the initial velocity will affect the final velocity, final ejection velocity?
I think the reporter believe that the initial velocity won't affect the ejection velocities, because as we calculate the.
Okay, thank you. I noticed that for tube design, it's shaped in a direct angle. Have you, what defines the 10 degrees and 25 degrees angle? Do you mind elaborating on that?
Because we actually we make six bending angles, but the angle of 5 and the 30 angles is the boundaries of the spaghetti to eject.
However, have you done experiments on having the curvature for the tube? Did you know what I mean?
Yes.
Have you considered that as part of your other conditions?
Time's up.
honorable juries, fellow debaters, and esteemed guests. This is the reviewer from Team GGWP reviewing the topic spaghetti accelerator. So this is the problem statement, and their focus is on the mechanism behind this phenomenon and the relevant parameters. This is the summary of the report, and the theory that they focuses on are energy transformation, transition, deflection equation, and force analysis. And their experiments has a force gauge that pushes the spaghetti in a consistent force. And for the preliminary experiment, they talked about Young's modulus, friction coefficient, fracture length. And for the pros and cons of the reporter, the reporter has conducted rigorous experiments, has done clear equation derivation and subtle consideration on different parameters, and also has a precise use of force gauge, which I believe is a good parameter. And for the cons, they do not provide condition to prove that it can be leveraging, as I stated in my question, and they lack boundary conditions stating that under what conditions can the spaghetti be launched. For the opponent, the consideration of deviation of equation is well done. However, they lack consideration on other parameters. The discussion, the opponent talks about have you collected spaghetti pieces, and then the reporter shows their results. And for another one is the opponent asks how do you do the simulation, and the reporter responds with using tracker and tracking the velocity of spaghetti at the front end of the spaghetti. As for the opponent, said again, well, the angle change where the spaghetti go, and the reporter proves it by showing all their tubes. And the reviewer, I asked about the rotation and spinning after ejection, and the reporter responds with the spaghetti bounces connector, and the connector energy is included for the rotational energy. The next discussion I talked about is if you use cantilever beam, there should be one fixed point, and a reporter does not really clear up this rumor. So the last one is the correlation between initial velocity and final velocity, and the reporter says that it wouldn't affect. However, I'd like to question this by saying, why would you control the initial force if you think that the initial velocity does not affect the final ejection speed? Here are some missing points that the reviewer would like to suggest. And the first one is shear force. Because from the observation, we can see that there's clearly vibration between the spaghettis. This vibration will cause shear force, which will be also affected into the kinetic energy. And I know you mentioned about the boundary conditions, but you failed to define specifically under certain conditions, what spaghetti launches. And as I talked about, the rotation and spinning of the spaghetti will definitely be affected in the kinetic energy, and you need to list out all the kinetic energies in your experimental formulas. The next point I want to add is about the cylindrical. Because when you're twisting or bending or pushing shear force into the spaghetti, there will be different kind of effects on the result of the spaghetti cylindrical aspect, which I think you need to further prove this in order to suggest your theory. And the last one is, I noticed that you mentioned all your tubes are 3D printed. However, there's definitely going to be a lot of frictions inside of the 3D printed tubes, and have you guys considered that into your overall experiments? And this is all. Thank you.
This is our concluding remarks. First, the spaghetti breaks into multiple pieces because of the vibrations. But in our experiments, the bending tube will decrease the vibrations. So the spaghetti will only break into 2 pieces. And in our analysis, include the considerations of the frictions. The reviewer mentioned that the 3D printed tube will cause the frictions to be different, and that is one of our parameters because we make the their heights of the printed tube to be different, and that the friction to be different. And the third is the spaghetti breaks off after the bending angles, and meaning the first half of the bending tubes won't cause any impacts on the ejection or breakoff. And fourth, we had an error analysis to base our conversions, so our experiments will fit the theory line. The fifth is we did have a point fix, so there wouldn't be any contradictories using the cantilever beam theories. because the inside of the bending angles, as you can see, here is the point that fits. The spaghetti will only change this point. So we can use this beam series. And we did contact experimental to find the bending angles boundaries, which is the 5 degrees and 30 degrees we mentioned in our experiment and mentioned in the report. And because of can we use the blackboard, please? Because of the 5 degrees will kind of like that. So the spaghetti will like this, and the 30 degrees will like this, and the spaghetti will break at here before the spaghetti is ejecting a little bit.
That is up. Time for jury. Any question or comment?
I have a comment about actually the model provided by the reporter. Because once you integrate the strength energy stored in the spaghetti, it seems that our belief that the energy is widely distributed over the entire spaghetti. But once it's break, then the energy is just locally released. Then how do you quantify how much ratio of energy can be transferred to the spaghetti? To the broken place.
We calculate by in our experiment data. Let me rephrase my answers. In our experimental data, we can see it is lower than when the convert ratio is 1, and we adjust the theory line by fitting the experimental data, and we calculate and find that the convert ratio will be nearly close to 0.75.
So we just directly divide by the fraction of the kinetic energy over the total potential energy of the spaghetti.
Yes.
Then how about yours?
Do you mean like how much percentage of the kinetic energy transferred? We believe that once it actually like stops at the point of ratio, and then I think the convert ratio is pretty I would say it's pretty rather good. Yeah, it's pretty close. Yeah.
I think I will need to the material of the and I can think of a coding loop and coding it to now the effects. But I think it's a very big one.
Can we answer more? Like, approaching 25 of the energy will be converted into the fracture energy and the heat energy. So that is the energy loss in our experiments.
Okay, any other? Even no marking time. Okay, for reporter. Seven, 8, 9, 6. For opponent. 5, 4, 5, 7, 5. For reviewer. 7, 7, 7, 8, Thanks all for your good job. Have a nice lunchtime.